So the purpose of our experiment is to manipulate sound waves by changing the medium and seeing how the sound waves change. So we have a device that calculates the distance via echolocation. So if I turn it on and point it at the wall, that laser represents where it's measuring to. And if you can hear, there's a clicking. And so it uses those clicks to measure how long it took for the sound to come out of the device to the wall and back to the device to measure the distance that it is between the wall and the device.
And we're hypothesizing that with an increase of temperature, the reading will be bigger because an increase of temperature, the molecules will vibrate quicker, the sound waves will travel quicker through a higher temperature.
We chose this hypothesis because if the sound waves are moving faster, they can go a farther distance in the same time. So say this is the room temperature time. In the time that it takes them to go there and back, if the sound waves are going faster, they can go farther distance there and back in the same amount of time, but the device will read a greater distance. Mm-hmm. So instead of actually changing the temperature of the environment, we are changing the temperature of the device. So we're kind of tricking it, making it think that it's in a warmer room, and then we are going to see how the distance measured differs, even though we're going to be calculating the exact same distance.
We'll be having 3 trials, one for the room temperature, one for a hotter temperature, and one for a cooler temperature.
So this is our setup. Our device is right here, and this is the distance that we are measuring. This is the wall that it is going to, and as you can see, the laser is right here.
244 centimeters. So right over here we have a pink tape, and each time we're going to put the device right behind it so that we'll measure the same distance each trial.
This is the first trial. The device reads 22 degrees Celsius, and the distance is 2.57 meters.
So right now we're warming up the device.
So the device feels warmer, it should be ready to go. So after heating the device at the fireplace, we now have it surrounded by heat in these containers.
So right now we can see that it's at 27 degrees Celsius. And it is 2.63 meters.
Now we're going to put it in the freezer to cool down.
We'll let it settle there for a few minutes and it should be cold.
Now the device reads 13 degrees Celsius, so I think we're good.
So we don't want the temperature to change too much, so that's why we're keeping some of the frozen treats around it.
Okay, it's still at 13 degrees Celsius. Let's see what the reading. Okay, 2.56 meters. Now we're going to summarize our data. So the actual distance that we measured with the measuring tape was 2.44 meters. And then our trial 1, which was the room temperature, was 22 degrees Celsius. And the device measured 2.57 meters. Our second trial was the hot trial, and it was 27 degrees Celsius. And the device read 2.63 meters. And then our third trial was the cold trial, 13 degrees Celsius at 2.56 meters. So as we can see here, the hot trial read a greater distance than the room temperature trial, which is what we hypothesized.
So because the lower temperature shows a shorter distance, we can see that for sound waves it will travel slower with a lower temperature because there is a lower amount of energy present.
So there definitely is a difference between the different mediums that sound travel.